Okay, welcome back. In this video, we're going to continue the discussion of limits in indeterminate forms, but before doing that, I want to show you a magic trick. This is something you can show your parents, you can show your friends, you can freak people out, and it's particularly timely. We're going to prove that 1 is equal to 2. You may say, you're going to prove something that stupid? Yep. Show you the proof. You're going to like it. I'm going to start with a true statement. What I'm about to write down is not the problem, okay? This is not the error that's going to be done in the calculation. I'm going to start with writing a true statement, A equals B, that these two things are the same thing. Next thing I'm going to do is I'm going to do something that we are always permitted to do in mathematics. We're always permitted to multiply both sides of an expression by the same number. Like I can multiply both sides by 2. 2a is equal to 2b. You know, if $1 is equal to $1, then $2 is equal to $2. And if we start with a statement that everyone agrees is true, I can double both sides of that statement, and who's going to disagree? You can't argue with that. I'm not going to use 2 though. I'm going to use b. And I multiply both sides by b, because b is just a number. So a times b is equal to b times b. b times b is b squared. Next thing I'm going to do is I'm going to subtract the same number from both sides. Like I could subtract 1 from both sides, or subtract 10 from both sides. If I got a pile of 100 pebbles and a pile of another 100 pebbles, so it's a group of people, we all count the pebbles. Yeah, I agree, there's 100 there, there's 100 there. If I subtract 10 from one side and also subtract 10 from the other, and everyone agrees that we both subtracted 10 from both sides, I subtracted 10 from both sides, everyone agrees on that, then we don't have to count it again. We know for certain that there's 90 in one and there's 90 in the other one. I mean, they're still equal to each other. So I'm not going to subtract 10, I'm going to subtract a squared. A times b minus a squared, whatever a squared is just a number, equals b squared minus a squared. Okay, next thing I'm going to do is I'm going to factor. On the left hand side, I'm going to common factor. I'm going to common factor an a out. A times b minus a. That's what you're left with when you do the factoring. On the right hand side, that's a difference of squares. We already saw how to factor that. It's b minus a times b plus a. All right, now, what are we going to do? Hey, we got a b minus a on both sides. And what do we do when we have the same thing on both sides? We cancel it, right? Cancel, cancel. So now I have a times 1 equals 1 times b plus a. And, a is equal to b. Like, we all agreed at the beginning. There's 100 pebbles on that side, 100 pebbles on the other side. Everyone agreed. It's still true. So what I'm going to do is I'm going to replace that b with an a. So a is equal to a plus a. Well, a plus a, that's like terms, that's 2a. Now I'm going to divide both sides by a. A over a is 1. 2a over a is 2. I said I was going to prove that 1 is equal to 2, but I actually proved that. Never mind, I did it. I thought I had the order wrong, but that's right. And it wouldn't have mattered even if it was a different order. Okay, proven. So everything you learn about math is wrong. Pack it in. Let's just call it quits. Why bother doing any of this stuff if 1 is equal to 2? Except there's a mistake. Where is it? I've had classes where I'll sit there for 40 minutes and wait. I won't leave until the class is over. I'll leave, okay, I'll come back next time back to this, unless someone tells me between where the mistake is. I've given this to teachers, high school teachers, in workshops. So find the mistake. I'll tell you where the mistake is. I'm not going to sit here on my own in a video for 40 minutes. Well, who's going to tell me? The mistake's here. There's an error in that line. And the line when we go from here to there. And the error is the division. When we cancel, we are dividing. Both sides by b minus a. So what? Okay, what is b minus a if a is equal to b? If b equals a, then b minus a equals 0. When we cancel, b minus a, we are dividing by 0. And that's why this happened. That's how serious it is to divide by 0. Everything breaks. So in some of the previous examples where I made a big deal and said, okay, we're going to cancel this, but it's only true if this piece isn't 0, if h isn't 0, or if this other thing, x minus 2 is not 0. This is why. Because it's not a silly thing. It's not me being picky. It's not like something we can ignore. It's serious, serious, serious. Division by 0 causes problems. And it causes problems in software. If you don't look for it, if you don't look for possibilities of division by 0, you can have software that completely breaks. Show a loved one. Show your mom, show your dad. Show them that 1 is equal to 2 and make them find the mistake. Anyway. So this idea that division by 0 being a problem, and this earlier idea of indeterminate forms, so expressions that have 0 on top and 0 on the bottom, and the possibility that that can yield something, that's actually pretty remarkable. That's not a trivial thing. The way that we will handle indeterminate forms is we'll use a set of strategies to see is it possible to extract what the answer is. What we'll do is we'll take the original function that we're given and we'll modify it in some way. We'll replace it with a function that's equivalent everywhere to the original except at exactly a. So for example, we'll factor. Like in this example, we start with a function that's 0 over 0 at x equals 3, so indeterminate. What we'll do is we will replace it with a function that's equivalent everywhere except at 3. So x minus 3, difference of squares, x minus 3 times x plus 3 over x minus 3. So I haven't yet replaced it. I'm going to cancel except at x equals 3, except where we would be dividing by 0. And then we have limit x approaches 3 of x plus 3, which is 3 plus 3, which is 6, just to redo this one again. So we replace the function by something equivalent to it except at the value, at the precise value that the limit is approaching. And then we took the limit of that replacement. So we'll go through a set of examples where sometimes we have to do that and sometimes we don't. First one here. If we just plug in the number, if we treat this like an evaluation, we'll get 0 on top and 0 on the bottom. This is indeterminate. It's saying, I am not going to tell you that easily. You can't just plug it in. There's something else you got to do. And we've already done what we have to do. Kind of. We have to factor. So I'm going to factor the denominator this time, because that's the quadratic part. That's the part that can be factored. We'll have x minus 4 over x minus 4 times x plus 4. And the x minus 4 can cancel top and bottom, except at x equals 4, where we would be dividing by 0 when we do that cancellation. So I'll have the limit as x approaches 4 of 1 over x plus 4, which is 1 over 4 plus 4, which is 1 over 8. That's our answer. So f of almost 4 equals almost 1 over 8. So it comes out of this. Even though it looks like 0 over 0, it's actually equal to something in the limit. Okay, next one, go top right. Let's plug in 4. We get 4 plus 4 over 16 minus 16. We get 8 over 0. This is not indeterminate. Eight over 0 is undefined. There's no way that we can recover an answer. If it was 0 over 0, there's a chance we can actually recover an answer. If it's 8 over 0 or 2 over 0 or 1 over 0 or negative 7 over 0 or anything like that, that's it. There's no answer. We will usually use the terminology, the limit does not exist. Does not exist. D N E. We use that as our shorthand notation, D N E. Okay, let's go to the one on the bottom left now. Let's plug in 4. We get 4 minus 4 over 16 plus 16, which is 0 divided by 32. Now that's just 0. That's it. 0 pizza shared with your 32 best friends. Everyone gets nothing. You're allowed to divide 0 by anything except 0. So that's a number. That's not indeterminate. It's nice. Okay, last one, bottom right. Let's just try to plug it in. It's 4 plus 4 over 16 plus 16. So 8 over 32, which is 1 over 4, which is also just a number. And that's also all we have to do. We just have to treat it like an evaluation because nothing weird happened. The only one example on this page that we had to do more work for was the first one, where we got a 0 on top and a 0 on the bottom. In other situations, we don't have to do extra work. Okay, we'll do some related ones. Limit x approaches 3 of what's there. It factors, but let's make sure we have to factor it. So this is going to be 9 minus 3 minus 6. Well, that's 0 on top over 9 minus 9. So we're going to get 0 over 0. That's indeterminate. It's more work. The more work is to factor. Limit x approaches 3 of x over x minus 3 times x plus 3. We'll use a product and sum method. I want mystery numbers. So looking at the top two brackets, I want mystery numbers that multiply to give me minus 6 and add to give me negative 1. The answer will be minus 3 and plus 2 as my factors. And notice that we have an x minus 3 on the top and x minus 3 on the bottom, so we can cancel those. For x not equal to 3, we can do that cancellation, we can do that division. So I'm looking at x values that are almost 3 because I'm taking a limit. X plus 2 over x plus 3. Now we plug that in. 3 plus 2 over 3 plus 3. We get 5 over 6. And that's our answer. When x is almost 3, that expression's output, its y value, is almost 5 over 6. Okay, next one, top right. We're going to get 0 minus 0 over 0 minus 0. We're going to get 0 over 0. So indeterminate. More work. This time it's there is a quadratic upstairs, and there's a quadratic downstairs, but it's easier to common factor. So I'm going to common factor each one. I'll common factor an x out on top, so 15 minus x. I'll common factor an x on the bottom, x times x minus 3. And then I'm going to cancel the x's. That cancellation is true for x not equal to 0. Now I'm going to take the limit of what's left. So we get 15 minus 0 over 0 minus 3. So that's 15 divided by negative 3, which is negative 5. Something important that I've been doing, and I haven't mentioned, is I've been keeping the LIM x arrow number. I'm keeping the limit operation in the intermediate steps. And that's actually important. That's telling us that we haven't taken a limit yet. Haven't taken a limit yet. We only get rid of that operation once we replace the x value by the number of the limit. So every single time, go back and look at the note. Go back and look at how all the examples have been done. As soon as we replace the x, that's when the limit operation disappears. It follows us every other step along the way, and it's important to do that. All right, bottom right. Let's see if we have to do anything fancy. Yeah, it factors, but maybe we don't have to. 0 minus 3 over 0 minus 9. Negative 3 over negative 9 is positive 1/3. That's it. Didn't have to factor. Even though we can factor, doesn't mean we have to factor. So no need to factor. Not 0 over 0. Only do the extra work if you have to. If we didn't have to interrogate this function. We asked it, hey, what's your y value when x is 0? It's like 1/3. Problem? Whereas the other two were like, ain't talking. So we had to factor them. Okay, next one. Will it talk? Or will we have to make it talk? 16 minus 16 over square root of 16 is 4. 4 minus 4. 0 over 0. We have to make it talk. It's indeterminate. More work. Show you the trick. I'll show you a trick. I think I already showed you the trick, but neat trick. That a minus b can be written as the square root of a minus the square root of b multiplied by the square root of a plus the square root of b. It's like a difference of squares, except the things aren't squared. This is only true for a and b positive, for a greater than 0 and b greater than 0. But what we have here is we have x approaching 16, so x is larger than 0, and we have 16 being subtracted, and 16 is greater than 0, so it's perfectly safe to use this trick. So I'm going to factor the top. Even though it's not a quadratic, I'm still going to factor it. Equals limit x approaches 16 of square root of x minus 4 times the square root of x plus 4. So some homework is to FOIL that out and confirm that that factoring is actually true. And it is, but confirm it on your own. Divided by the square root of x minus 4. So I'm going to cancel this. Top and bottom. 4 square root of x not equal to 4. Or if you want, for x not equal to 16. Now I'm going to continue with the limit. So that's the square root of 16 plus 4, which is 4 plus 4, which is 8. So that one really did not want to tell us what its y value is. or what it's almost equal to when x is almost 16. We didn't want to say, well, we found it anyway. That won't always happen. There's in future classes, in future calculus classes, you may come across a function that's a little bit tougher than these. You have to do something other than factoring. Oh wait, here's one right now. How are you going to factor this? How are you going to answer this question? Well, let's first make sure we have to do something fancy. Maybe we'll just plug in the 0, limit h approaches 0 this. So we have the square root of 1 plus 0 minus 1 divided by 0. So I'm replacing all the h's with zeros. Square root of 1 minus 1 over 0. Square root of 1 is 1, so I have 1 minus 1 over 0. I have a 0 over 0. This is an indeterminate form. And that means we have more work to do. If we can't factor, what are we supposed to do? Like I've given you one tool. I've given you a hammer. And now you're off looking, everything has to be a nail, because that's all you have is a hammer. Now we've come across something that's not a nail. You take out the hammer and you're like, now what? Well, you use a more powerful tool. I'm going to write it down. You'll be shocked at how powerful this is. You may not be ready to see this. If there's small children in the room, you may want to hide them so they don't witness this powerful technique. Okay, ready? Bam. We're done. We solved it. It's fixed. Multiplied by 1. And it's legitimately one of the most powerful things in mathematics, is to multiply by 1. It is remarkable how many problems, complex problems in theoretical physics, fluid dynamics, and a variety of other areas have been solved by the multiplication of the correct form of 1. You can't use any old 1. You gotta pick the right one. You gotta pick the right type of 1. Like 10 over 10 is certainly 1. You could use that. But I'm gonna use something that will actually work. So here's the one I'm going to use. I'm going to use the square root of 1 plus h plus 1. But to keep it equal to 1, I have to have the same thing in the denominator. So square root of 1 plus h plus 1. That's 1. Okay, that's 1. How I obtained that is I took the part of the expression with the square root, whether it's in the top or the bottom does not matter. I made a copy of it, and I changed the minus sign in between the pieces into a plus sign. And then I made sure that the top and bottom both have that thing. Because if they don't both have that thing, then that thing's not multiplication by 1, and I have changed the function. So notice that multiplying by 1 does not actually change anything. All I'm doing is I'm replacing the function by something that is potentially not the same at h equals 0, but is the same everywhere else. Now what I've done so far is it's even the same at h is equal to 0, but let's see what happens as we simplify. So square root of 1 plus h minus 1. Bottom we have h. I'll maintain the color scheme. Square root of 1 plus h plus 1. Square root of 1 plus h plus 1. Now we'll FOIL the top. So I have the root of 1 plus h times the root of 1 plus h. That's the first part of the FOIL. Now the second part of the FOIL is outside times outside. Plus the square root of 1 plus h times 1. And then minus 1 times the square root of 1 plus h for inside times inside. And then last times last. minus 1 times 1. And then the bottom, I recommend not expanding that out, just leaving it as h multiplied by that bracket. Right, now notice that those two middle terms on top cancel. I have a root of h, I have 1 plus h root minus 1 plus h inside the root. So that's going to cancel with that. I also have root a times root a equals a. So root 1 plus h times the root of 1 plus h just equals 1 plus h. So I have a 1 plus h here. And then I have a minus 1 from the 1 times 1, all divided by h times the square. I'm going to drop the color scheme now. 1 plus h plus 1. Okay, I have a plus 1 and a minus 1. Those are going to cancel. So limit h approaches 0 of h over h times 1 plus h. Oh, forgot the square root. And now the h's top and bottom are going to cancel for h not equal to 0. So now we've replaced the function by an equivalent function except at exactly the value of the limit. Now we can take the limit as h approaches 0 of 1 over what's left, 1 over the square root of 1 plus h plus 1. Now we're just going to replace the h with almost 1, or almost 0. That's essentially the same thing as plugging in 0. So 1 divided by the square root of 1 plus 0 plus 1, which is 1 over 1 plus 1, which is 1/2. And that's the answer. Whew! That was not very nice, was it? But the trick, which by the way I didn't invent, some extremely smart person would have been the first person to think of multiplication by 1 using this particular form of 1, and the rest of us just say, hey, that worked. I'm going to copy you. I'm going to copy what works. Humans are pretty good at that. Seeing what works and copying it, modifying it, making it better. One of our traits. So anyways, we went through and recycled someone's trick, and it worked out. It gave us the value of the limit. It told us what the 0 over 0 was actually hiding, what the value of the function is when the value of the function almost is equal to when h is almost equal to 0. We'll stop there. See you in the next video series.